Hi guys. In this video, I want to go over the relationship between a Riemann sum, specifically the limit as n goes to infinity of a Riemann sum, and a definite integral. So this video is going to focus on the relationship between the Riemann sum and the definite integral, and it assumes that you already have some knowledge of what a Riemann sum is, what a definite integral is. I'm going to go over it briefly anyway, just in case you've seen it but you don't quite fully understand it. And the whole purpose of this is to answer questions such as, if you're given the definite integral, can you write this as an equivalent Riemann sum? Or if you're given a Riemann sum, can you write this as the equivalent definite integral? Okay, so let's start with kind of a refresher on what a definite integral measures and what a Riemann sum actually is. So if I want to go from A to B, basically I want the integral from A to B of f of x dx. What does that represent on the graph? Well, if we draw a vertical line from A up to the function curve and do the same thing with B, the area represents, the definite integral represents the area under the curve from A to B. So whatever this blue area is, and it's just going to be some numeric value. We could have units. It could be square feet or square meters or some type of square unit of measuring area. And that would be the answer to the definite integral. Okay, so that's what a definite integral means graphically. Now let's go back. What about the Riemann sum? So the Riemann sum comes from basically an estimate. So I want to estimate the area between the curve and the x-axis by drawing a bunch of rectangles and then adding up the sum of those rectangles to get an estimate of what the area is. Okay, so for our purposes here, we're going to use what's called a right Riemann sum, which means the top right corner of every rectangle aligns with the function curve. So the top right corner of each rectangle is on the function curve itself. Okay, so my right Riemann sum setup would look something like this. And the idea is, if we just add the area of each individual rectangle, we're going to get an approximation of the area between the function and the x-axis, which is what the definite integral represents. Now, if we use more rectangles, if we make them narrower, we're going to get a more accurate approximation. And if we take the limit as the number of rectangles goes to infinity, then we get the exact area between the curve and the x-axis, which will give us the same answer as if we evaluate the definite integral. Okay, so the Riemann sum is basically the sum of each of these rectangles. And what we're going to do for practical purposes, we want to make sure all the rectangles have an equal width. And we're going to call that width delta x. Okay, so if I add up the area of each rectangle, I'm going to get, so let's call this rectangle 1, 2, 3, 4, 5. So the area of each rectangle is length times width, or we could think about it as width times height in this case, since the rectangles are kind of tall. So we could think of width times height. So let me set this equal to the exact area. Okay, so the definite integral gives the exact area, and the Riemann sum will give an approximate area. So I'll use the squarely equal sign. And we're just going to add up the areas of each individual rectangle. So the width of every rectangle is going to be delta x. So the area of this first rectangle is going to be delta x times the height. Well, what's the height of this rectangle? Well, the height is equal to the function value. So it's going to be f of some x. Now, what x? So what we're going to do at a, we're going to call that x sub 0. And at b, we're going to call that x sub n. Okay, and then we're going to add 1 each time we go over 1 delta x all along the x-axis. So this would be x sub 1. This would be x sub 2. This would be x sub 3. This would be x sub 4. And n would be 5 in this case. So x sub n or x sub 5 doesn't matter. Okay, so the area of the first rectangle is, okay, since this is x sub 1, and this is the function value at x sub 1, the height of this first rectangle is going to be f of x sub 1. Plus, and then we need the height, or the area of the second rectangle. So the width of the second rectangle is delta x. And the height of the second rectangle would be the function value at this x sub 2 plus f of x sub 2 dot dot dot, and we add up all 5 rectangles. Okay, and the height of the fifth rectangle would be x sub n. Now, we don't want to have to write out the width times height for every single rectangle. So what we're going to do is we're going to convert this to summation notation. So we're going to have some k that starts at 1 and counts along. And so it's going to just go through each rectangle and sum up the area for each one. So whatever our current x is, that will be x sub k. So x sub k is our current x. So k goes from 1 to n. So when k is 1, we're using this value. When k is 2, we're using this value. When k is 3, we're using this value. When k is 4, we're using this value. And when k is 5, we're using this value. Okay, the delta x will be the same for all of these. And we can just say f of x sub k. Okay, so that gives us our approximate area based on a Riemann sum with n rectangles. Now, if we want the exact area, we just take the limit of that as the number of rectangles goes to infinity. Of delta x times f of x sub k. Okay, now before we relate these two formulas, the two formulas for area, one using the definite integral and the other using the Riemann sum, there's a couple more things I want to break down in the formula. I want to break down the delta x and the x sub k. So let's see if we can come up with kind of a more detailed description of delta x, kind of a breakdown here. What does delta x equal in terms of b, a, and n? Well, delta x is the width of each rectangle, which is going to be equal to the total width of the interval, which is given by b minus a. B minus a gives the total width of the interval, and then we're going to break that down into n rectangles of equal width. So we're just going to divide that by n. Now, if you want to look at the specific example for the way I've drawn this diagram, delta x would be what? B is, let's go ahead and, let's say that I didn't draw in the scale for this graph, but let's go ahead and say at least the x-axis is a scale of 1. So each of these tick marks is 1. So we have x equals 1, 2, 3, 4, 5, 6, 7. Okay, so you can see that b is 7, minus a, which you can see is 2, divided by n, the number of rectangles, or the number of subdivisions, which is 5. Okay, so the total width of the interval is 7 minus 2, which is 5. And we have 5 rectangles within that interval. So the width of each rectangle would be 1, which we can see from the delta x I've drawn right here. It's the distance between 3 and 4, which is 1. Okay, so the formula works. Now let's take a look at x sub k. Okay, the idea here is we start at x sub 0, which starts at a, the lower bound of our interval, and we go up by 1 delta x each time. Okay, and how many times do we go up by 1 delta x? K times. So x sub k, we're going to start at a, and then we're going to add a bunch of delta x's. How many delta x's are we going to add? K delta x's. Okay, so let's take a look at the way I've drawn it in the diagram and see if it works for our example. X sub k equals a, which is 2, plus k, which, okay, I've drawn x sub k right here. So we've gone up 1, 2, 3. So k is 3 in this case, times our delta x, which is 1. So 2 plus 3 is 5. So based on the way I've drawn this diagram, x sub k should be 5, which you can see that it is. Okay, so the formula works. And one final thing, we have this delta x within our x sub k formula. I want to go ahead and substitute the breakdown to break down x sub k even more. So finally, we're going to end up with x sub k is equal to a plus k times b minus a over n. And now we're finally ready to write the equation that's going to relate the definite integral to the infinite limit of the Riemann sum. All right, so we have the integral from a to b of f of x dx is equal to the limit as n goes to infinity of the summation k equals 1 to n of, now delta x, we're going to use this formula that we came up with. So we're going to say, instead of delta x, we're going to say b minus a over n times f of x sub k. But we're going to use this expression for our x sub k. So it's going to be f of that whole expression, f of a plus k b minus a over n. Okay, so this is the final equation that relates the definite integral form to the infinite limit of the Riemann sum form. And we're going to be answering questions where we're given the area in terms of a definite integral, and we're going to have to convert that to Riemann sum form, or vice versa. We're given the Riemann sum form, and we have to convert that to the definite integral. Now, one more thing I want to say is that this b minus a over n term does not depend on k. See, k is going from 1 to n, so k is changing. This b minus a over n term does not depend on k changing at all, which means it doesn't have to be inside of the summation. So we can also write this integral from a to b f of x dx equals limit as n goes to infinity of b minus a over n times the summation k equals 1 to n of f of a plus k times b minus a over n. Okay, so sometimes we're going to want to use this version on bottom, and sometimes we're going to want to use this version on top. It just depends on the question and the form that they give you. Okay, now let's look at some specific examples, starting with this one. So write the definite integral from 2 to 9 of 3x to the 6 dx as a limit of a Riemann sum. So we start with the formula from the previous slide, and then we can go ahead and start writing down things that we know. So we know a is 2. Okay, that's given here. We know that b is 9. That's given here. And we also know that f of x is equal to 3x to the 6th. That's given here. Okay, so now let's plug in what we can into the right side of the equation, the Riemann sum side. So we have the limit as n goes to infinity of the summation k equals 1 to n, b minus a over n. So b is 9, a is 2, 9 minus 2 is 7. We get 7 over n. And now f of a plus kb minus a over n. Whenever you're doing a substitution, I always tell my students, pay attention to the parentheses. You see how this entire expression, a plus k times b minus a over n, is within these parentheses, and this is our f function. Now we have the definition of our f function over here, and in these parentheses is just x. So what does that mean when we do the substitution? It means we take this 3x to the 6th, and whenever we see x, this part in parentheses, we're going to replace it with this part in parentheses, the a plus k b minus a over n. Okay? So what this is going to become is 3, and then instead of x, we're going to have a, which is 2, plus b minus a over n, we already determined was 7 over n. We're going to multiply that by k, so it's going to become 7k over n. Okay, and now finally we can clean it up a little bit. Limit as n goes to infinity. If we multiply this 3 times 7, we get 21 over n, and we could leave that on the inside, or we could pull it outside the summation. It really doesn't matter in this case. Let's go ahead and leave it on the inside. K equals 1 to n. Oh, I forgot the 6th power up here earlier. Sorry about that. So 3, and then all of this stuff to the 6th power. That's what we want. Okay, so back here, 21 over n, 2 plus 7k over n to the 6th power. And I would think that most instructors would allow you to leave your answer in this form. Too tedious to try to multiply that binomial out 6 times. So just this format should be fine. Okay, so that's kind of the easy one. Now let's look at an example that goes the opposite way, where we're given the Riemann sum, or the limit as n goes to infinity of the Riemann sum, and we need to write this as the definite integral. Okay, so this is all about pattern matching. I want to look at this. I want to compare it to this and look for patterns. So the first thing I notice is that this 5 over n kind of looks like the b minus a over n. So I can conclude, if I'm right about that, that b minus a equals 5. Okay, now it definitely looks like this 2 plus 5k over n is very similar to this a plus k times b minus a over n. So in this case, the a would be the 2. So let's say a equals 2. And then if I substitute 2 in here, I can easily find b. What minus 2 equals 5? That would be 7. And so comparing the 5k over n to the kb minus a over n, that doesn't really tell us anything. But now we need to figure out what f of x is. So we pattern matched this part with this part. Okay, so what's the difference here? In the formula, I see an f of some function, and in the given Riemann sum, I see an ln. So it makes sense for f of x to just be ln x. Okay, so then if I take this as my x, if I compare the part in parentheses here to the part in parentheses here, that means I take, whenever I see an x, I substitute this entire expression. So we'd end up with ln, and then once we plug in for a and b, it would be ln 2 plus 5k over n, which matches this perfectly. So we know we're on the right track. Okay, so now that I have a, b, and f of x, it's very easy to write the integral. We're going to end up with the final answer. The integral from 2 to 7 of ln x dx. Now, one way if you wanted to check your answer, you could go back to this method in the first example where we were given the definite integral, and we needed to convert it to a Riemann sum. So here, once we got the answer, we now have the definite integral. You could go ahead and use the same method from the previous example to convert this to a Riemann sum and see if you get this as your Riemann sum. And if you do, then you'll know that you've done it correctly. Okay, for the sake of time, I don't really want to check, so let's move on to this final example. Write the following as a definite integral. So here, before we move further, there's a typo here. This should say n. Okay, so we're given a limit of a series, but it's not written as a Riemann sum using summation notation. However, we could probably fix that. If we look at just this part here, the only thing that's changing is these numbers here. So 1, 2, 3, 4, all the way up to n. So I believe we could write this in summation notation. We would have the limit, n goes to infinity, 1 over n, and then the summation, k equals 1 to n, and it would be e to the 1 plus k over n. Okay, so when k is 1, we get e to the 1 plus 1 over n, which matches the first term. Then k goes to 2, we get e to the 1 plus 2 over n, which matches the second term, all the way up to n, where we would get e plus n over n, which matches the final term. Okay, so now we have it written as the infinite limit of a Riemann sum. Okay, now we can compare to this formula, and for this example, you can see that the b minus a over n part is actually outside the summation. So that's why in the first slide I gave you the two different versions of this equation. Just so you know, the delta x part, the b minus a over n, can be outside of the summation. So let's go ahead and start writing down what we know. So we know b minus a has to match this 1. So b minus a equals 1. And then we look for a pattern here. Okay, what do we see in the given Riemann sum that seems to match this pattern? To me, it definitely looks like this part. Okay, so if this pattern matches this, that means a would have to be 1. This a matches this 1. Okay, a is 1. And then if we substitute 1 for a here, b minus 1 equals 1. What minus 1 equals 1? B would have to be 2. Okay, and then k over n, so b minus a would be 2 minus 1, which is 1. K times 1 is k, so we would end up with k over n. So that matches as well. Okay, now, if we kind of say these parentheses match with these parentheses, and we compare this e to the power compared to this f, it makes sense that f of x would be e to the x. Okay, so the formula says the function has these arguments. So if it's e to the x and we use these arguments, we get e to the 1 plus k over n. So this all seems to match up, and now that we have a and b and f of x, we should be able to write the definite integral. So we have the integral from 1 to 2 of e to the x dx. And once again, if you wanted to check this, you could go in the opposite direction, convert it back into a Riemann sum, and it should match this exactly. And so that's a way that you can check your final answer.